All right, let's try that now. I'm crossing my fingers that that works. So give me an update if that sounds better. Oh, thank goodness. Oh, all right. And let me know if the video looks good, and then we'll go from there, and hopefully everything should be good now. All right. Cool. All right. Whew. That was a close one. All right, let's get started then. So let's aim to finish by about 10 o'clock on all these. So hopefully you got a chance to look at this and then try it out for yourself. I did make a couple of adjustments based on things that I noticed. For instance, on number 1, the angle was actually missing, so you need the angle to actually finish the problem. That was it. And on number 4, if you attempted that one, you could technically solve it. It ends up being a little bit more lengthy than I preferred it to be, because you actually needed to find something using a kinematic equation, which, yeah, it takes a little bit longer. So what I'm going to do for number 4 is, when we get there, I'm going to give you the time, basically. You could have found the time using kinematics and then solved the rest of the problem, but I'll give you the time when we get to that. So other than that, let's go ahead and run through them. So first one, so we have a handful of adventurers that went on a hike and pushed a 500 kilogram boulder out of the way of their path and accidentally pushed it over the edge. At some point while it's sliding down the 30-degree inclined hill, it experiences an acceleration of 0.25 meters per second squared in the direction along up the incline. What is the coefficient of kinetic friction? So what we're going to do is we're going to go here. So, one. And we have, here's the boulder. And we want to find the coefficient of kinetic friction. So we know that the coefficient of kinetic friction is only going to really pop up in one equation, so we ought to be writing that equation. We have that the friction force is equal to the coefficient times the normal force. So at the end of this, we do need to use this equation to get the coefficient of friction, so I'm just going to solve for it. Coefficient of friction equals the friction force divided by the normal force. And we don't have the value of either of them, but that's fine. We can use what we know about the forces in here to relate it to these forces that we want to find those. So let's start by finding these two forces. So I'm going to draw all my forces in the diagram. So I'm going to have, for instance, the weight going always straight down. We have a surface that the object is in contact with, so being in contact with the surface gives a normal force, whereas if you don't have a surface to be in contact with, there's no normal force. So normal force is perpendicular to the incline. And we also have that it slides down this incline, so we have a friction force that will resist it going up the incline along its surface like this. That's the friction kinetic force. I'm going to draw a coordinate system here to be specific about my x and y directions. So as usual, we will put the x-axis along the incline. So everything along this line is the x-axis. We'll put positive x down the incline like that. And the y-axis we're going to make perpendicular, going right through the mass like this, right along where the normal force should be. That's the positive y going above the object. Now, we have a force in this diagram which is off both axes, so we need to split it into components. So we're going to start from the mass, we're going to go along the y, and then we're going to stop so that we can draw a line that's parallel to the incline or to the x-axis, and that'll be our x component of that weight. Okay. We know that by putting the angle of the incline, let's use actually blue to indicate this. So here's the right triangle that makes up the incline. The angle of the incline is in the bottom corner here. We know that in this case we're going to set it to 30 degrees. And that if we break the vector into components here, you could use geometry to move it over, and you'll find that in this setup here, this top angle in that component triangle is theta. So now we're going to break up these components here using theta. So we have along the y-axis here, that should be mg cosine theta because it's the adjacent component, and along here, that's mg sine theta because it's the x component, because it's the opposite side rather. So let's take a look at this. We're going to find the friction force first. So let's find this. And in our drawing, we have the friction force along the x-axis, so we can relate to other forces along the x by using Newton's law. So we can say sum of forces along the x-axis equals mass times acceleration along the x-axis. We do have acceleration in this problem. In this case, I directly give it to you. So we're going to leave the right side alone for the time being. On the left side, I'm going to write in all the forces that have x components. So I have a total of 3 forces in this diagram, but only 2 of them have x components. So we have the friction force in the negative x direction. Notice how it's to the left of the to the left of the y-axis, which makes it negative. Whereas this component of the weight, mg sine theta, is to the right of the y-axis, so it makes it positive. So we're going to write positive mg sine theta and we're going to subtract off the friction from the opposite direction. Okay. We wanted to find the friction to get the answer to the problem, so we're going to solve for friction. So we get the kinetic friction force equals, we're going to swap places with the term on the right, and it's going to become mg sine theta minus max. Okay. So there we go, we have that there. We're going to take this, we're going to plug it back in where we need the friction over here. But I'm also going to go hunting for one more thing, which is the normal force, which is the other thing that we do not have the numerical value of. So we're also going to go find the normal force, and we're going to then look in the y direction on this to find the normal force. So sum of forces in the y equals mass times acceleration y. No motion is ever expected along the y-axis in the problem, so we can get rid of the y acceleration. Right side is 0. My sum of forces will account for 2 forces with the y component. So normal force being positive because it's above the x-axis, and we have the y component of the weight, which is mg cosine theta, which digs below the axis, so that means it's negative. So we're going to write n minus mg cosine theta equal to 0. We're going to solve for that normal force to go find that. So normal force is mg cosine theta. Okay, so now we take this, and we're going to plug it back in to find, we wanted the coefficient. Okay. So in the coefficient of friction, we're going to rewrite it. So we have mu k equals, so in the top, we're going to substitute what we found for the kinetic friction. which is going to be mg sine theta, and then we have minus max. In the denominator, for the normal force, we have here, we found the y direction, mg cosine theta. Okay. Now, we've plugged in everything, and we do have everything at this point. You could actually clean this up, if you want to, by realizing that the top has two terms, and they both have mass in it, which means you could factor it out of the top. And the bottom has mass as well, so you can cancel all the masses out of this problem. So you don't actually need the mass to do this. Now, the angle you however, do need, so we'll simplify this expression to coefficient equals g sine theta minus the acceleration divided by g cosine theta. Okay. So at this point, when you're plugging it in, you have everything, but you do have to be a little bit careful, because I did say in the problem that you do have an acceleration, but that acceleration is not down the incline. It doesn't go in the direction of motion, because we are expecting this boulder in this problem to slide down the incline. But I said that the acceleration is in the direction opposite to the motion up the incline. So the acceleration in this coordinate system is negative, to specify that it's up the incline. So I'm going to write on this term, so minus the value of ax itself, write it down here, is minus 0.25 meters per second squared. So the magnitude is 0.25. The direction is negative because it's up the incline. You'll get a double negative here, so it'll just cancel out, make it a positive, and then you divide it by g cosine. Cosine 30. Okay, so the value for the coefficient that you do get for this ends up being 0.607. I tried to design this problem reasonably, so that means this value for the coefficient is also very reasonable, because coefficients of friction are, generally speaking, less than 1 most of the time. Rarely over 1, but it's not impossible. So it's very, very reasonable, and also has no units if you analyze your units. Coefficients of friction do not have any units. Let me know if you have any questions on the first problem, and we'll take a look at the second one. Everything's good with everyone? All right. Second one is a circular motion problem. So you have a ball with a mass of 0.125 grams. It's attached to one end of a 25 centimeter long string while you hold the other end of the string. Assume that you twirl the string around in a circle vertically in such a way that the speed of the ball is 10 meters per second as it passes through the highest point in its path. We're going to find the tension in the string. So we're going to draw a vertical circle. We're going to place the object at the top of that said circle. And we want to find the tension, which is a force in there. So since we know it's circular motion and we want to find a force, we're just going to apply Newton's law, but we're going to remember what we do differently for the circular motion. So here is your circular path that you twirl the object in. Here's the center, I'll mark it with an X. And we know we have the object is at this moment in the top of this circular path. The string goes straight down to the center. Okay, so you're basically holding the string at one end and you're just twirling it around, so the ball just goes round and round and round and round. Now, because we are going to be discussing the forces and we're going to be using circular motion to solve this, we're going to draw our free body diagram in here. So we have the weight of that object because it has mass. Gravity's pulling it down. Always goes down. And the tension always is directed along the string or the rope away from the object. So we should have that the tension also goes down. Circular motion with forces implies that you should use Newton's law for a circle. So sum of forces in the radial direction towards the center of the circle equals MAR. Friendly reminder that in a circle, you should set a coordinate system which is based on what points towards the center or what points away from the center. My strong preference is to set positive towards the center. So anything that points to the center is positive. Makes the math a little bit nicer. There's less chance for mistakes when you do this. You could set negative to the center, but then you just have to set positive the other way. It turns out you have to account for a sign that you might not expect in a certain place, so it will cause an extra minus sign to be in there that will screw it up. So put positive toward the center and usually everything will work out just fine. So that means we have two forces and they both point towards the center, so if they point towards the center from the top, no matter where it is really, they're both positive. So we should write on my sum of the forces that positive tension and positive weight. Okay, and that's because it's toward center, which is positive. On the right side, circular motion always has acceleration because circular motion implies that you need to change your direction to continue to steer in a circle. Simply changing the direction is changing your velocity, which results in an acceleration. And that acceleration is the radial or centripetal acceleration, which is what's represented here. So it cannot be zero. Now in this case, because it's circular motion, we can say that it's v squared over r. We don't have the value of the acceleration, so we can just expand it as v squared over r. We need to solve for the tension, so we just go ahead and solve for the tension. So it's mv squared over r minus mg. The mass is common to both terms, but only on one side, so we're just going to factor it and it'll just clean it up a little bit, but we can't get rid of the mass. So v squared over r minus g when we factor that. Okay. For all this, pretty standard procedure, just plug in the numbers to all of this. And if you plug in all your numbers that are given in the problem, you will get 48.8 newtons. So this one's a pretty straightforward problem. This one you should definitely be sure to get. There are some circular motion problems that are a little bit more complex, but this one, once you realize it's just a vertical circle and you set up your forces, as long as you understand positive is toward the center and negative is away from the center, that's the only complication that happens in this. Any questions on this one? I'm assuming the video is better now. Like the string is just extra info that isn't needed. No, it is. It is definitely needed. Okay, so in here where you plug stuff in, the numbers that you would be plugging in are 0.125 kilograms. The velocity of this is 10 meters per second. Square it, and then your radius is the length of the string. You remember you're twirling the string around, so it's being swung in a circle. The string is the radius of the circle. So in this case, it would be 0.25 meters long. So then minus 9.8 meters per second squared. And this will yield your 48.8 there. Cool. All good. No worries. Yeah, no worries. That's what I'm here for. Okay, so let's take a look at number 3. So number 3, this one's another pretty standard problem. So you have a 2-mass system. They're basically connected by a string. So you have a 5 kilogram mass that sits on a frictionless surface. Okay, so here's your 5 kilogram mass on a frictionless surface, which is inclined, okay, 30 degrees, and it's connected to a 2 kilogram mass, so that's the other one over here, by a lightweight string that is wound over an ideal pulley, like this, and such that the 2 kilogram mass hangs freely, meaning basically there's nothing other than the string supporting it. And gravity pulling it down. There's nothing else interacting with it. We want to find what the acceleration of the hanging mass is. So I vaguely ask for the acceleration here. So it's implied that it is a linear acceleration, but it means to consider any acceleration in total that you would have on that object. Now, once you set up your coordinate system, you should realize that there's only an acceleration in one direction ultimately, or along one axis. So let's go ahead and let's draw that out real quick here. Okay. So now we have the inclined part and the vertical part here. That's the angle of the incline. Here's both of the masses and the string. Okay. All right. So we need to find the acceleration in the system. So there's only a couple ways you should be thinking of in terms of finding acceleration. It's either going to be kinematics, which is less relevant at this point in the class. It's still a possibility, but you should also be thinking of Newton's laws, where you can talk about the forces and relate that to the acceleration pretty easily. So we should draw all of our forces. So we have the weight on 1. We have the normal force because it's in contact with the surface and pushing into the surface, so the surface pushes perpendicular to the object, like that. We have the string attached to it, so the tension is along that string, like that, away from the object, T. And it's a frictionless incline, so that means we don't consider any friction on this one. The other mass, simpler. We have just the weight down and the tension in the string holding it up. Okay. Now, we want the acceleration on this second mass here, so what we're going to do is we're going to relate or link the forces on this mass together with the acceleration of that mass. So we're going to specify a coordinate system first before we do that. Your x-axis should be along the incline. I'm going to set positive x up along the incline in this problem. So positive y is perpendicular to it like that. And we're going to follow this, go up the incline, and we're going to turn it with this pulley. As we go over the pulley, the coordinate system rotates with it, and the positive x continues to flow downwards. Okay. So that's the most crucial part right there. The perpendicular direction, there's nothing happening, it's just all along the vertical direction, so that's all we're going to really care about. And since everything is happening along the x direction, that's where the acceleration is going to be. So that's the acceleration that we're going to find is ax. Now, if we do Newton's law on that, so sum of forces in the x equals mass 2 times acceleration in the x. We are finding acceleration, so we're going to leave the right side alone for sure. M2ax. Okay. So now we have two forces that go along the x-axis. Remember, positive is down on this coordinate system because it was up the incline here, so it's got to go up, around, and down. So that means what's down is positive, that's the weight, and what's up is negative, that's the tension. So we have the weight, m2g, minus the tension in the opposite direction in our coordinate system. We want to find the acceleration. You could divide off by the mass if you really wanted to, but I would advise not here because you're still missing the tension. So let's go get that tension first before we do anything with it. So let's find T on, so now we look for another place to find the tension. The tension's on the other mass, so we're going to consider mass 1. On mass 1, we need to make sure we have all of our x components laid out here. In this case, we have one force that's off the axis because we have the x-axis is along the incline, and the y-axis goes in like that. So we're going to split that into components. So we're going to go along the y-axis first, and then go parallel to the x-axis or the incline. So then that'll give us the other component. So we know that the angle of the incline will just be put into the top of that triangle when we do it that way. So we get on the y component, adjacent is mg cosine, and along the x component it's going to be mg sine because it's opposite to the angle. Okay, so now, sum of forces in the x direction on mass 1 is where the tension exists, so we're going to do that. Sum of forces in the x equals m1 ax. Leave the right side alone since we have acceleration. Mass 1 has acceleration because mass 2 has acceleration. They're connected together, so they have to do the same thing. So both accelerations are shared. Right side is left alone. We have, out of 3 forces in total on mass 1, there are 2 forces with an x component. We have the tension in the positive x, and we have a component of the weight going slightly leaning down the incline, so it's to the left of that y-axis, so it's negative m1g cosine theta. So minus m1g. Sorry, sine theta. Sine theta. Okay. So we needed to find the tension to get that acceleration over here, so we're going to solve for the tension and plug it back into where we needed it. So the tension is m1ax plus m1g sine theta. So let's take that expression here, and let's just drop it back into where we needed it. So now let's copy this expression exactly the way it is and just replace the tension. So we're going to get, starting from the left, we have m2g minus, now you have a term, but it has multiple things that are going to be substituted. You ought to put parentheses anytime you substitute something because the minus sign is going to have to be distributed. So we're going to distribute the minus sign to the following. We have T is m1ax plus m1g sine theta. So that's the entire term for the tension here. And then we're going to set it to the right side, which is m2ax. Okay. So that's plugging in the tension into that. And now what we're going to do is we're going to go back to the original goal, which was to find the acceleration on that hanging mass. So we're going to solve for AX. But in solving for AX, you're going to then realize, okay, I have two places where AX exists. So we need to move them together first and pull it out as one single thing. So first of all, this minus sign here would need to be distributed, both terms. So technically both terms are negative, so we have minus that first term minus the second term. I'm going to move this first term over to collect it with the other one so it becomes positive on the right side, and I'm going to write what's left. So we have, starting from the left, m2g. This term is moved over, and then we had distributed the minus sign here, so it's going to be minus m1g sine theta equals, right side, we have m2ax plus the term we moved over, which is m1ax. So that's the two terms that we had. We've collected them, so what we're going to do is we're just going to factor them out and move the rest of the stuff over. So now finally, when we factor it out, you have m1 plus m2, both times ax. Just divide the stuff over. So therefore, ax equals all the stuff on the left, m2g minus m1g sine theta divided by m1 plus m2. Okay. This is the final expression for the acceleration. With this alone, you'll get 4 out of 5 points. But now we plug in. You check the units on everything, you'll get kilogram meters per second squared on the first term in the top, kilogram meters per second again. That makes newtons in the top, divided by kilograms in the bottom. That'll give you an acceleration in meters per second squared. If you don't have a habit of plugging in your units when you plug in your numbers, just be warned that you won't have any ability to check the reasonability of your answer for that. So units are good for checking if something is, if it's a valid expression or not. So if your units for some reason don't work out here, it tells you that you did your algebra wrong. So it's a good idea to put your units in. Now, all the values we're going to plug into this problem, we're just going to plug in the two masses. M1 is the one on the incline, which is 5, and M2 is the hanging mass, which was 2. So we're going to just drop in those values, and I already have it calculated out. So 2 times 9.8 minus the second term is 5, 9.8 sine 30 is a half, divided by both masses added together in the bottom is just 7. And what you'll get for this acceleration is a value of negative 0.7 meters per second squared. Okay. So this answer is negative because it means that the system is accelerating in the negative direction for both masses. For the hanging mass, the positive is pointing down. So that means that if the acceleration is negative, it's accelerating upwards. And for mass 1, it means that it's accelerating down its incline rather than up the incline. Now, acceleration doesn't automatically mean that's the direction it's moving. That's the direction it's tending to move in. So what that then translates to is, for instance, if mass 2 was moving down, then an acceleration in the opposite direction doesn't mean it's moving up. It just means it's slowing down because it's being tugged more up than it is down. Or on this mass on the incline, if it was moving up the incline, then an acceleration down the incline just means it's again slowing down while still moving up. The other option is that maybe both masses are moving up and then the other one's moving down the incline in the direction of the acceleration. So there are two possibilities to what the system could be doing, but keep in mind that acceleration does not automatically mean that is the way it's moving at that instant. So let me know if you have any questions on solving Newton's laws with putting multiple masses together. This one is a pretty standard problem, so make sure you know how to definitely do the ones with pulleys where the objects are connected together. So those are very important problems to know. Okay. All right. I would consider number 4 in here to be the harder one out of all of them, in my opinion. Mostly due to the fact that you weren't originally given the time, but I'm going to just give the time in this one to make it a doable problem in the space that there is. It's not that you can't find the time on your own with kinematics equations, it's just a little bit it's extra work and lengthy, so I'm going to assume in time that's given. I already calculated it out, and I'll just assume it in the problem. So this one is also based on a real-life scenario, so if you've ever driven between Camarillo and Thousand Oaks, then you'll know that there's a giant hill there, and these measurements are actually real to life. I made the measurements on the maps, so the values you get are pretty realistic. So you have a 1540 kilogram electric car that can supply a force in the direction of motion to do work, in this case to move up a hill between Camarillo and Thousand Oaks. So we're going to basically draw some incline between 2 points. Assume the car is only working against gravity. Okay, so this is a way of saying that there's, like, if you have things like friction or any other forces you're thinking of, don't consider it. We're only going to consider that the car supplies a force in the direction of motion to do work, and that is only opposed by gravity. Okay. The car travels a distance of 3.7 kilometers and rises through 206 meters in elevation. Okay, so that's vertical distance. How much power must the car supply? Okay, so we're still talking about the car here. How much power is the car supplying? So it has to do with this force it supplies to keep it moving up the hill, starting with the speed of 20 meters per second at the bottom and finishing with 30 meters per second at the top. So this one, we're going to have a couple of possible approaches that you could take. There is a much more ideal approach that you would want to be taking here. Okay? There is the time that I'm going to just give in this problem to make it doable in the space that you have there. So use a time of 148 seconds. Okay? So if you do the kinematics, if you actually did it yourself, you would actually find it's 148 seconds. If you were able to do that, good for you. I keep on hearing big bangs going off in the background. It's either Ariana Grande doing Bang Bang, or it's someone partying very hard before the 4th of July, so it's not acceptable. So problem 4, I'm going to add in the time interval to do this is 148 seconds. So here is the easiest way to approach this problem, is realizing that you already have a lot of information that will give you all the energies of the system, basically. You know the height it rises through. That's potential energy. You know how fast it's going at the start and how fast it's going at the end. That's kinetic energy. You just want to go with conservation of energy to keep it as simple as possible. There is one more route you could take, which is more to do with the work done, because the idea with this problem is, we'll set it up here in a second. But once you set it up, at the end of this, you have to remember that power is the amount of work divided by the time interval that the work is done over. And work is just the transfer of energy, so for all intents and purposes, you could just think of it as energy just goes to the top. Now, you would be inclined to say, okay, well, I could talk about work as force done, over some distance. And you would be right to do that. The thing is that you'll probably end up with a little bit longer of a problem if you do force times distance and then you go that route. You could also just realize that work is closely connected to all the energies you're talking about, and it's much easier to talk about the energies. So, in the picture, we have the bottom and the top. We have Camarillo. We have Thousand Oaks. We have some distances here. So, for instance, the distance along the incline is the distance we're traveling by car, which is, call it distance D, is 3,700 meters to Thousand Oaks. And then the altitude that we rise through is the vertical distance. So that vertical distance we'll call H, and it's 206 meters. Now, using these distances here that are given in this triangle, we could already just find the angle if we need it. So I'm going to write in the angle theta, but I'm not going to get it unless I know that I need it. So let's go off to the side here and let's see if we need the angle. So power is work done over time. Specifically, it is the power supplied by the car. So in other words, the power that's associated with that force applied F, that we're going to call it. And it's the work done by that force F, which is supplied by the car. So in my free body diagram, so if we consider a particular point that the car is at anywhere along this incline, we have the weight down, we have the normal force perpendicular, and we also said, based on the problem, that there is only a force applied by the car in the direction of motion, so it's up the incline, only opposed by gravity. So this is it. And here's how it's only opposed by gravity, is because if you try to move the car upwards with some force up the incline like this, there should be only one force in this diagram which will hold it back from doing that, which it's not going to be the normal force because it's perpendicular to the motion. There is a component of the weight or gravity that actually pulls it down the incline, and that's what we mean by it's only opposed by gravity. Now, we're going to find the power that the car needs to supply, which is the power associated with that force F. So we need to find the work done by that force F. Now, again, two routes. You could do force times distance, but then you need to go find that force, and it's a little bit longer to go that route. However, you can relate that to the energy, so we're going to use the conservation of energy theorem, since we already know a lot about the energy. So, conservation of energy states the total energy of the system after our final, so K final plus U final, equals the total energy we had in the system initially, K initial plus U initial. But that's what we call mechanical energy, so K plus U, or kinetic plus potential, is mechanical energy. The mechanical energy final only equals the mechanical energy in the beginning if there is no work done by non-conservative forces, which in general you account for by writing that term on the initial side. So now, remember that there are only two things, at least in this point in mechanics, that are considered conservative. The gravitational force and the spring force. Those are the two things that we write the potential energy for. Any other force in here is considered to be non-conservative. So in this force diagram here, there are three forces that could be doing work on the object. There's the force applied, by the car. There's the normal force, and there's the weight of the car. The gravitational force, or the weight, is considered conservative. That's one of the two. The other two here, the normal force and the force applied, are not conservative. It's not one of those two forces. So we are going to consider the work done by the normal force and the work done by the applied force. The work done by the normal force is 0 because it's perpendicular to the motion. Work is only going to be based on the parallel component of the force to the direction of motion. So there's no work done because it's perpendicular to the motion. The force F, however, is already parallel entirely to the motion. There is 100% of its force in the direction of motion. So there is work done by that for sure. So that means that this work, non-conservative, is only going to be the work done by the applied force F. So in the next line here, we will write it as the work done by the force F. It would technically be plus the work done by the normal force, but we're really going to scratch it out to 0. For the rest of this, the energies. At the bottom, we have no potential energy with respect to where we're going to set y equal to 0, which is at the bottom. Pretty sensible. So the lowest point we're going to set as 0. So no height off the y equals 0 at the beginning means there's no potential energy initially, since it's only based on height. Kinetic energy, we got 20 meters per second going for us at this point, so we're going to say that there is kinetic energy since it's based on movement. Potential energy final, we have a height of 206 above the y equals 0, so we do have potential energy, gravitational, and we do have a final speed of 30 meters per second, so we also have kinetic energy. So now, we're going to write what we have here, we're just going to expand it out from left to right, so kinetic energy final is 1/2 mv final squared plus, next term. Potential energy final is gravitational only, so it's mgy final, or mgh, equals. Kinetic energy initial is 1/2 mv initial squared, and then plus your work done by that force F, which is the only non-conservative work that you have. All we have to do to solve this problem is to solve for this work done by that force F, and that just belongs in the power formulation. That's it. So the work done by the force F, we'll just subtract this term over. So it's 1/2 mv final squared plus mgy final minus 1/2 mv initial squared. Okay. So using the values in here of the mass of the car, which was given to be 1540 kilograms, V final is taken to be 30 meters per second. V initial is taken to be 20. And we're just going to plug in those values, along with y. Y final is 206. Okay. Plug all these values in, and you're going to get the following for the work done by the force F. The work done by the force F is 3.49 times 10 to the 6th joules of energy. So in other words, about 3.5 million joules. We take all that work done and we plug it in to here. We divide by the time. So therefore, power done by that force F is that value divided by the given time, or you could have found it using kinematics if you were really on top of it. So then we do 148 seconds. And the power that we get here is going to be 2.36 times 10 to the 4th watts, or joules per second. So the simplest approach to this problem is to just use conservation of energy, since we already know a lot about the energy of the system. Any questions on this? let's see here, 5. All right, so that's halfway through that. I would actually argue that we're probably more than halfway done because the later problems are a little bit quicker. So should finish by 10. Number 5. A popular roller coaster ride has riders in a cart. The total mass is given to be 2,000. At the top of a 100-meter tall tower, so in this diagram right here, they're released from rest and come to a 200-meter horizontal section. Okay, so that's this little section here. We want to know how fast is the cart moving after that section. So the cart starts at the top of the tower. You release them from rest. They have nowhere to go but down according to gravity. They slide down across the 200-meter section, and I just want to know how fast they are going at this point at the end of that section there. This one you'll find to be surprisingly easy. So here's that section that's 200 meters long, and there's a point up here which is 100 meters in height. From the horizontal section. So they start at the top of the tower here, and they slide down this track and go all the way over to this point right here. So that's where they end up. So that's the final, and this is the initial. Okay. This problem gives you the information about the height, which ties directly into potential energy, gravitational potential energy, and the final position over here, we're finding a velocity, which is the kinetic energy, really. So we're going to relate the energies of the system together, and that's just conservation of energy. So now, that then means when we use conservation of energy, final equals the initial, k final plus u final equals k initial plus u initial, plus any work non-conservative if you have to consider it. In this problem, there is only one non-conservative force that is at play in here, which is the normal force. The only other force that's responsible for any motion is gravity pulling it down the hill. So if that's the case, the normal force is considered non-conservative, but it's always perpendicular to the motion in this case. So there is no work to consider by non-conservative forces. Okay, keep it simple. Now we are going to scratch out a couple of terms. First, we have no initial velocity. Velocity is directly tied into the kinetic energy, so we have no initial kinetic energy. We do have a height, so we do have gravitational potential energy. In the end of this, though, we end at the bottom of this problem, which we will define to be y equals 0. So then we cross out the final potential energy because the height is 0, which gives no gravitational potential energy, since it's only based on height. Kinetic energy, we are expecting movement at the end that we're going to solve for, so we're going to leave that alone. And we're just going to write the remaining stuff expanded out. The kinetic energy is 1/2 mv squared, so this is final, equals, remaining term on the right side is the gravitational potential energy, mgy, in this case initial. The mass appears in every term on both sides, so we can just cancel that out. So it does not depend on the mass of that cart. We solve for v final, and we just find it simply to be the square root of 2gy initial. You plug in those numbers for that. Y initial is 100. And the speed, V final, ends up being 44.3 meters per second. Okay. So this one's a pretty straightforward problem. Once you recognize that's conservation of energy, very straightforward problem. So make sure you definitely know how to do problems that are similar to this kind of problem. So on a practice test that you may have already done from class, there is a problem which has a swing on it, and I would argue that that swing problem is very similar to this problem because you only have to deal with heights and movement, so it just exchange between potential and kinetic energy. It's as simple as that. So you have the question, can you explain briefly why work non-conservative is 0 again? Okay, so when you consider, so let me write this out. When considering non-conservative. Okay, so when you consider the work done by non-conservative forces, so W and C, the consideration that you take into place is first to identify what forces you have in the problem. So 1, identify all forces at play between initial and final. Okay. So that means in here, in this problem, you're going to consider all forces that you see acting on that object from when it starts up here to all the way when it ends up down there. So there are only 2 forces that are at play in this entire problem. You could pick any point to draw them. Now, I'm going to do it at the bottom, and you're going to see why it's not going to matter so much when you do the top section either. So down here, it's just the weight and the normal force. Okay. So you have those 2 down there. Now, even if you took a very obscure point, the one that just doesn't seem like a good choice to analyze, even if you picked like this point right on when you're on the inclined surface, when it's transitioning between vertical and horizontal, you could still argue the same thing. What we're considering here is not really going to care so much about, the point that you pick in here. As long as you can identify all the forces, you can still tell which ones are conservative and non-conservative. Regardless of the point that you chose here, when you see this, there's only 2. There are only 2 conservative forces to consider at this point in mechanics, and your 2 conservative forces will be based on what you're going to do here. So let's write this. Conservative forces are only one of the 2, gravitational and spring. Okay? Again, only to this point in mechanics. There's technically something else that happens, probably not in this class, but if you go on further, you may run into one more conservative force, but we're not going to care about it now. Okay? So for the time being, it's those 2. In this problem, you have 1 conservative force. It is the gravitational force, mg. However, everything else is non-conservative. Okay. Now that means in this problem that the normal force is considered non-conservative. But now why is the work non-conservative 0? Is because the work done by that force is 0. So number 1, you have to have a non-conservative force to begin with. If it doesn't exist, then it's just automatically 0. But even if you have a non-conservative force, like the normal force, well, the normal force is always perpendicular to the motion. So since work is only based on forces that are parallel to the motion, then the work done by the normal force is going to be 0. So then 3, finally, when you do this, is their work done by the non-conservative forces. Okay? This is what you should process conceptually. You don't have to, like, I'm not trying to give you a lot of stuff to cram into your head, but if you want the precise way of determining why it's either 0 or it's not 0 in a particular problem, this is the precise way of arriving at that conclusion properly. So that's why in this case we're going to say work non-conservative is 0. So normal force, but does no work. Perpendicular to motion. Okay. So hopefully that fully clarifies what you do with the work non-conservative term if you don't usually use it. Hopefully this will answer where you use it and where you don't use it. Cool. Any other questions on this problem or anything else related to conservation of energy? Okay. All right. Number 6. A firework is launched into the air and briefly comes to rest at the highest point in its path. Okay, so we're going to consider something at rest. At that moment, it explodes into 2 fragments. Masses are given, 0.25 and 0.75. The larger piece, 0.75 kilograms, is found to be moving with a maximum speed of 20 meters per second. So you know how fast the larger piece is moving. This is immediately after the explosion. What is the amount of power generated from the explosion if it occurs over a time of 50 milliseconds? Okay. So let's start with the question itself. What is the power generated in this explosion? Okay, so let's not get super distracted about, all the different possible things you could use in this problem to attempt to solve it. Let's focus on the goal for right now. The goal is to find the power. So we're going to write the expression for the power first, based on its definition. So the definition of power is that it's work done over time. So power equals work over time. Okay. Friendly reminder to make sure make sure you take some time up to the side. This only takes like 15 or 20 minutes to do, but it'll help you a lot if you haven't solidified this. Take the time to go through all the formulas that you could possibly use, all the concepts. Make sure you understand what each thing in each formula represents and the type of scenarios that you would use it in. But at least make sure you know what each thing is, because, for instance, you'll use P for power, but there's also P for momentum, because apparently the P is silent, right? Right? P is silent. So you use P for momentum, and you need to distinguish that from your P for power. So this is the definition of power. So we have a couple ways to get the work done. Now, work, you could use its definition, which is force, times velocity. Force times the distance. And now the thing is that you don't really know too much about the force and the distance that you would use in this problem, so it doesn't sound very good. Previously, in another problem, we also realized that we can talk about work in connection with different forms of energy. So in other words, we could use the conservation of energy to solve for the work done if we have sufficient information to do that. This problem, it sounds like it might be a possibility, but there is one more route that you could take, which is actually still based on conservation of energy, but it's much more compact. And I think in this case, the one that you would much prefer to go with is that the total work done is just the change in kinetic energy. Okay, Okay, so from here to here, all I said is that the net work done on a system is equal to the change in kinetic energy. That is also known as the work energy theorem. Okay? The work energy theorem is the more compact version of what you formally use as the conservation of energy, where you talk explicitly about kinetic, potential energy, and the work non-conservative. It is the same thing, just more compact. But in this case, the work done in exploding the pieces apart from each other and having them separate apart is pretty much the only thing to consider. So we just simply change work to change in kinetic energy. So as long as I know what the change in kinetic energy is, I can find that answer. Now, how do I get my change in kinetic energy? Well, to get my change in kinetic energy, which is of the system, it's implied, it's of the entire system. The system is composed of two pieces. So you have to take the kinetic energy of the system, final, minus the kinetic energy of the system, initial. Now, we know that initially you have the two pieces together. It's at the top of the path, so you have a firework that's at the top of the path, and it is at rest. So that means, since kinetic energy is only based on movement, we're going to cross out that. Okay, so everything is at rest initially, since it's at the top of the path and at rest. The kinetic energy of the system final is going to be the kinetic energy once it has exploded. So it will acquire a velocity, and hence will have a kinetic energy in the end. But there are two pieces. So you now have to write the kinetic energy of two pieces, which is just simply the kinetic energy of one final plus the kinetic energy of two final. We write out the kinetic energy for each term, 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So in order to solve this problem, we just need to know both velocities. We already know both masses. We do know one of the velocities, but not the other. So you do need one more principle to solve this to get the other velocity. So let's assume that in this diagram here, okay, so I have the two pieces of the firework breaking off here. Okay. So here's something exploding apart. Unnecessary artsy details. Okay. And one piece goes one way and the other piece goes the other way. So they push apart. So let's call this piece on the right M2 and this piece on the left M1. Now, I'm going to arbitrarily assign a mass to M1 and M2. It doesn't matter which one is which as long as you are consistent, just like with your units, just be consistent. I'm going to call mass 1 the first mass that I listed in the problem, which was 0.25. So this one is 0.25 kilograms, and I'm going to assume then the other one is 0.75 kilograms. Now, once you've developed or established which one's 1 and which one's 2, you're now going to assign the velocity to the correct one. So for instance, in the problem, I state that the larger piece is found to be moving with a speed of 20 meters per second. So that means mass 2, which I've called the larger piece, has to be associated with that 20 meters per second. So that's V2 final equals 20 meters per second. The other one is unknown, but we can find this pretty easily by knowing one principle. This problem should remind you of another problem, which is the ice skater problem, where two people will start in contact and they'll push off of each other and it'll propel each other in the opposite direction in an ice rink. That's an example of conservation of momentum, where you have for every action there's an equal and opposite reaction. And whenever you're applying Newton's third law, equal and opposite reaction, conservation of momentum can be applied in that situation. You can actually derive from equal and opposite reaction what the conservation of momentum formula is. So this is like the two ice skates pushing off each other. So we're going to apply the conservation of momentum here. So equal and opposite reaction. Okay. So if you had to ask conceptually, for instance, what's the amount of force of one compared to the other, they both feel the same force because it's the same explosion. The accelerations will be different because of their masses, though. So we have conservation of momentum. And that states the total momentum of the system before, so in other words, momentum being mass times velocity, so m1, v1 initial, that's the momentum of 1, plus the momentum of 2, so m2, v2 initial. That gives us the total momentum of the entire system before the explosion. It's equal to what it is after, so we're going to do the same thing after. m1, v1 final plus m2, v2 final. Now, we know that in the system, it starts at rest initially, so we can cross out both initial velocities conveniently. Okay. System at rest. Okay. That means we're just going to work with what we have after. We're going to solve for V1 final in our case. So V1 final, when you move the stuff around, so when you move this term over and divide off by the mass, you'll get that V1 final equals negative m2 over m1 times V1 or V2 final. Okay. So just move that around. I have written it in a different format for the purpose of highlighting the fact that I technically don't need to give you the masses. I only need to give you how big one mass is compared to the other. So for instance, in this problem, I tell you that one of them is 0.75 and the other is 0.25. That means that ultimately one mass is 3 times bigger than the other. So in here, when you write this m2 over m1, or anywhere you really see that, it only matters how big is one compared to the other. So I could use 3 and 1, it would be the same as plugging in 0.75 and 0.25. So I just need to tell you how big one is compared to the other. In this case, it is 3 times bigger, so 0.75 kilograms divided by 0.25 kilograms gives you 3 times the velocity of the bigger piece, which was 20 meters per second, and 3 times 20 is 60. Now this is a velocity, so you will get negative 60, and that's only because of the coordinate system. So this indicates it's in the opposite direction. Okay. Now let's go back to the original goal. We needed this speed here so that we can calculate the change in kinetic energy of the system and hence get the power that's produced in the explosion. So we could, plug into all of this stuff here. So given that you now know what M1 and M2 is, and you know what V1 final and V2 final is, just plug it all in and calculate it. What you will get upon calculating that is an answer of the change in kinetic energy of the system being 600 joules of energy. That energy is released in a very short time, which was given, which is 50 milliseconds. So then the power, P, is that energy divided by 50 milliseconds. So you could quote unquote convert that, but I would advise you to just realize that milli is 10 to the minus 3 in value. So you can literally just write 50 times whatever the prefix is worth, which is 10 to the minus 3 seconds in the entire bottom. So for this, you'll get that the final answer is the power produced is 1.2 times 10 to the 4th watts. Okay? Or in other words, 12 kilowatts of power. Okay. Any questions on problem 6? Okay. I would also argue that this is probably the other problem that was maybe a little bit more difficult in the sense that there's a couple of things you have to realize to be able to solve the problem. Starting the problem, you should have just realized that you start with the power equation, but one of the connections that you need to make is that work can be represented as a change in kinetic energy when you're talking about the work done on the entire system. So you could use that, and from there it's not too bad. Once you realize that you need to calculate the change in kinetic energy, you'll be missing the velocity, and you'll hopefully know that in this problem, the principle that is applied is the conservation of momentum. Okay. Number 7, we have a carnival ride that consists of a rotating disc. The diameter is 8 meters, and the mass of that ride is 2,000 kilograms. It allows 8 thrill seekers, riders. Each of their masses are taken to be 60 kilograms. They sit in seats which are not along the circumference, but rather at a distance of 3 meters from the center. This picture here shown depicts that you have the entire system. The diameter is 8 meters, and that means that the radius is 4 meters. The more important thing is the radius here, since you use that in pretty much everything. 4 meters, but the riders sit at a distance of 3 meters from the center, so that's what the drawing kind of illustrates here. But that's hopefully what you would have pictured just by reading the question. The ride is spinning, right? So spinning automatically should tell you, hey, angular speed, angular velocity. That's the Greek letter omega that everybody says is a W, but it's Greek letter omega. It's spinning at a rate of 40 revolutions per minute. We'll deal with those units in a second. And it slows down with a constant angular acceleration until it comes to rest in 20 seconds. I want to know what the tangential acceleration felt by the riders is. Okay. So, the tangential acceleration is a type of linear acceleration in a rotating system. The formula is pretty easy to just pull out, but you should also understand what it is in the diagram. So I'm going to quickly sketch out a circular motion diagram which will show you where the tangential acceleration is located and how that compares to other acceleration you may have in the problem, and why it's important to know what it means. Okay, so you have, in this case, I'm only going to draw a circular path. I'm not going to draw the whole thing, just so I can give more focus to a couple of details here. Here's a circular path with the center marked here. And I have that something is on that circular path. That thing could be anything. In this diagram, you should recognize that there are 2 main axes in a circle in regard to where you're located. There's one axis which extends directly out of the center of the circle through the mass and out. Since that axis lies along the radius, we call that the radial axis. The term that is often used along this axis is the term centripetal. So anything that is centripetal The term literally means center seeking, which essentially translates to things along the radial axis. The other axis has to be perpendicular to that, so the axis that's perpendicular is the one that just barely touches the edge of the circle and goes parallel to the circle and then goes back away from it like that. That is the tangent line, or also known as the tangential axis. In terms of the things that you should understand conceptually in circular or rotational motion are the following quantities. You have a velocity at which you revolve around a circle. So first of all, you have a spin of the entire system. So the spin is usually represented by this curved arrow. You have the Greek letter omega, which represents the angular speed or angular velocity. Okay, that's how fast it's spinning. And because the system is spinning or something is rotating, this mass or whatever this is revolves around in whichever way it's spinning. But it does have a velocity at any given instant. So let's say in this diagram, if it was counterclockwise, the tangential velocity, as we would call it, is the velocity that points in the direction it travels at the exact instant, which lies along the tangential axis. Call it VT, and that's the tangential velocity. Okay, so conceptually you should know that. Now as for the accelerations that are more relevant to this question. The accelerations are going to be two of them that are linear that we're going to talk about. One of them is the only acceleration you need to steer into a circle and travel at constant speed. That's the radial acceleration, or also known as the centripetal acceleration. That points towards the center. It's abbreviated AR or AC. Now, you have your centripetal or radial acceleration, which I don't care about in this particular problem, but you're going to then distinguish that from what we call tangential acceleration, which is the acceleration along the tangential axis. And it can have one of two possibilities in the problem. It will either point in the direction of motion to speed up the motion, or it'll point against the motion to slow it down. So in this problem, because you know that the ride is spinning initially at its maximum rate, given the problem, and it slows down to rest in a certain amount of time, you know it has to slow down. So if you had to draw this in a diagram, the tangential acceleration would point opposite to the direction of the velocity. So this would be AT. The equation for the tangential acceleration is very simple. AT equals R times alpha, the angular acceleration. Okay. So in order to get that tangential acceleration, you need to know what the angular acceleration is. The angular acceleration is closely related to the angular velocity, which is all kinematics quantities. So we're going to consider rotational kinematics. So in rotational kinematics, you're going to consider that there are three major kinematics equations as before. These will be the three that you want to pay attention to. So if you know those three kinematic equations and you're solving a rotational kinematics problem, you'll be fine with those as long as the acceleration stays constant, which in these problems that we're considering, we're going to take everything to be constant or an average. So these are the three golden equations that you need to consider. There are 5 quantities that you can write out of these equations, so I'll list them all. Delta theta, that's the angular displacement. Omega initial is the angular velocity initial. Same as final, angular acceleration, alpha, and the time. In this problem, we have that the time elapsed is 20 seconds between the first and the second event, which is going from spinning to not spinning. So initially, it is spinning at a given rate. The given rate is not in radians per second, which is what it should normally be in. It's in revolutions per minute. Now, you could, in theory, leave the units the way they are in any case, but you need to make sure that they are consistent and they yield the result that you want in the correct units. If you want to be safe, put it in radians per second. So 40 revolutions per minute, we'll use the following conversion factor. So you'll have 1 revolution on the bottom to cancel out the revolution on the top. You'll have 2 pi. You can write radians in there on the top, so rad, and then convert the minutes to seconds. And what you'll get for this is, upon converting that properly, you should get 4.19 radians per second. Okay. Now, that's the initial angular velocity, so we're going to fill that in there, 4.19 radians per second. We don't know how much angle the system turns through. The angle can be given in radians by default, or it could be given in revolutions or even degrees. But that would have to be the total angle that the system spins in 20 seconds, which we do not know. We do know the angular speed initial. We know what it is final. It's at rest. It's not spinning anymore. And we don't know the angular acceleration, but we want to find that so that we can plug it back into the tangential acceleration. So we're going to avoid using the angular displacement since we don't know it, which means we're going to use this first kinematic equation. That's going to be omega final equals omega initial plus alpha delta t. You can clean it up by just getting rid of your final angular velocity, because it's 0 at rest. You solve for alpha, which is minus omega initial over delta t, which is minus 4.19 radians per second divided by 20 seconds, and you'll get that the angular acceleration is minus 0.209 radians per second squared. So we have this angular acceleration. Now the minus tells you that the system is slowing down because it is an acceleration. It's just rotational acceleration. It represents the acceleration to its spin rate. So the spin rate is slowing down in this case. Now that's of course assuming that it is spinning in the positive direction. That is normally the assumption we're going to make here. But the plus and minus is just going to be based on the coordinate system regardless. Now, now we take that angular acceleration and we plug it back into the tangential acceleration, and we get that AT is, now the radius, you can either think between 3 and 4 meters, but the system is a radius of 4 meters because the diameter is 8 meters. But the people, the riders, what they experience is not 4 meters. They're sitting at 3 meters, and they're going in a 3 meter radius circle. So then times this. Keep in mind that radian is a placeholder unit. It has no technical value because it is only there to remind you what type of angle it's expressed as. It's not actually a unit that you consider. So we write it as 1. Okay, so it's 1 over seconds squared. Now, the units will end up being meters per second squared, and the answer you get for this is then minus 0.628 meters per second squared. Okay? And then again, the negative represents that it is slowing down the system. Any questions on this one? There is one detail I am going to point out here, since I am here because this is a question that sometimes gets asked. The one detail I'm going to point out, and this has to do with part of why I drew out this drawing, is you will notice that there are technically 2 accelerations in the problem. Okay, so again, pay a little bit more attention here. Because there are two types of linear accelerations that you could consider in circular motion, you do have to be specific about which acceleration you want. So the problem is either going to specify, hey, let's find the tangential acceleration, or hey, let's find the centripetal or radial acceleration. Okay, so it's one or the other. But there is one question which is vague, but it means something else. The vague question would be, quote, what is the acceleration in the system? So if they ask that, when they say acceleration in absence of the word rotational, or angular. So if they don't say angular acceleration, what they mean is linear acceleration. But if they just say acceleration, what they mean is find the total acceleration on that object. So that means if you can consider both radial and tangential acceleration both in a system, and it's just asking for the acceleration, it means find both and put them together. So in this setup, putting them together would imply that you have one component and another component, and when you want to put two components together that are in completely different axes, you have to do Pythagorean Theorem. So if you wanted to do a hypothetical question where it asks for the total acceleration, you have to split it into components, which it's already split for you, and you just do Pythagorean Theorem with those two components. So if you needed to find the total, here's how you would do it. A equals the square root of AT squared plus AR squared. Okay? If you have that question, that's what they mean by find the acceleration in the system, is to then consider both if you have both. So just a little extra tidbit, just in case. And that's hence why I drew the diagram, because otherwise, why would you think of doing that if you don't know why they're, how would you know to do that if you don't know that they're pointing in different directions? So that you can only figure that out if you know that they're pointing perpendicular to each other. And we're going to go on to the final one here. So again, let me know if you have any questions and we'll finish off here. Final question. A tire with a radius of 0.508 meters and a mass of 15 kilograms rolls without slipping along a road with a car that is moving at a speed of 30 meters per second. If the tire can be modeled as a solid disc, what is the total kinetic energy of the tire? Okay. This problem is similar to the previous ones that I've made, so you can actually consider it to be like the bowling ball question. Now, to do this one, we're going to consider that the rolling motion without slipping is a combination of two kinds of motion. The two kinds of motion are going to be composed of rotational, because it's spinning, and linear motion, because it is also technically moving along a line, which is the road in this case. Before I carry on, there is a problem that you need to make sure you know how to do similar in regard to this kind of question, which is actually to apply the conservation of energy. If you have to apply the conservation of energy in a system that is spinning or rotating in any form, then that means you must consider both translational or linear and rotational kinetic energy. So anywhere you talk about kinetic energy with something that has the ability to rotate, you have to consider two kinds of kinetic energy. So that means the total kinetic energy of the system is translational, linear, plus rotational. Translational is as before, which is 1/2 mv squared, but we're going to call it V center of mass, so VCM, and that's how fast the center of mass of the system, in other words, like in this case, the center of the tire, moves along the line. So how fast does it do that? Plus 1/2 I omega squared, which is the spin rate. We need to remember that omega and the velocity of the center of mass are very closely tied together when we have rolling motion without slipping. When the object rolls along the surface, this rolls and spins with some angular speed omega, this rolling motion will translate, or I guess let's use a different word, this rolling motion will automatically imply linear motion as it turns and rolls to the right like this. So if you track the center point of this system, the center point actually follows a straight line parallel to the ground in this case, and it has a velocity called v center of mass. Okay? And that velocity is just the radius of that system times its angular velocity omega. We can use this because in this problem I only give you the velocity of the center of mass. It's how far or how fast the car is moving in this case, because the wheel or the tire is attached to the car, and as the car moves forward, the wheel rotates and rolls along the ground like this. Okay? So that means if I only give you the velocity here and I don't give you how fast it's spinning, you just use this to link them. So what I'm going to do is I'm going to put omega, the spin rate, in terms of v. Simultaneously, I'm also going to plug in the moment of inertia of this system. The moment of inertia of this system is based on the fact that I tell you that it is going to be modeled as a solid disk. So you look up the moment of inertia. It's a given formula. In this case, for a solid disk, it'll be 1/2 mr squared. So let's write this out. We have equals 1/2 mv center of mass squared plus 1/2. We're going to substitute the moment of inertia to be 1/2 mr squared for the disk. So that's the moment of inertia of disk. Okay. And we're going to substitute omega as the relation to the linear speed of the center of mass. So we're going to replace it with omega equals v center of mass divided by r. So v center of mass divided by r, and don't forget that it is squared. Okay. Now with this, you could plug in the numbers, but there are simplifications that you can make so you can avoid chances of making mistakes here when you calculate it. So the simplification is that because this entire thing here is squared, so it's v squared over r squared, the r's will all cancel out. That leaves you with the following: 1/2 mv center of mass squared plus the second term, you can collect the 1/2 and it's 1/4 m, and it'll be just v center of mass squared. Okay. This is really nice because it just simplifies to 3/4 m v center mass squared. Because a half plus a fourth is 3/4. You can just plug in all this information. So 3/4 of a 15 kilogram tire times the velocity of the center of mass, which is 30 meters per second. Don't forget to square it. And you get that the total kinetic energy of the system, finally, is 1.01 times 10 to the 4th joules. Let me know if you have any questions on this one, and we'll wrap everything up. And then I'll quickly announce a couple of things before we end. Any last questions before we wrap it up? All right. So tomorrow you all have the exam. So tomorrow morning, the in-person review for one more practice test. I want to make one more version. I'm going to do my best to make that last version closer to the difficulty of the exam and also the concepts that you'll most likely encounter. So we'll go over that tomorrow. It's going to be at 11. Okay, so 11 because of the people who are in labs, so there's more of you in labs. So we'll start at 11, same room, and we'll go over another version. Another version will be made right now. So if you hang tight for about an hour, hour and a half at most, check my website again and you'll find the last version uploaded into there. So check that, and then we'll go over that tomorrow. If you have any other questions, email me. I have a couple of emails to catch up on too, so email me any questions you have remaining, and otherwise I'll either see you tomorrow. Best wishes, and don't overdo it. There is such a thing as overdoing it, so make sure you get a good amount of sleep, because I've been in a place where I've almost not slept at all for exam. It's not good. So keep yourself healthy at least. Try to do that. So otherwise, best wishes and good luck.